Ever stop and think about what's keeping your feet planted firmly on the ground? Or what keeps the moon locked in its endless dance around the Earth? It's this invisible, silent force that, well, literally runs the entire universe. And today, we're going to pull back the curtain on this master force, gravitation. So, here's our game plan. We're going to start with Isaac Newton's famous aha moment with the apple. Then we'll unpack the universal law he figured out. After that, we'll bring it all back down to Earth, talk about free fall, clear up the super common mix-up between mass and weight, and finish up by seeing how gravity's pull is the reason huge ships can actually float. All right, our story starts with probably one of the most legendary light bulb moments in the history of science. It's all about how Isaac Newton connected a super simple, everyday thing with the grand clockwork motion of the heavens. So this was the big puzzle that Newton was chewing on. You know, he sees an apple just drop, straight down. Simple enough. But then he looks up at the moon, and it just seems to hang there, right? Circling and circling. How on earth could those two things possibly be connected? Well, Newton had a hunch. They were just two sides of the same coin. And this was Newton's incredible leap of logic. He thought, what if the exact same force that's pulling that apple out of the tree is also pulling on the moon? What if that's what's keeping it from just flying off into deep space? This was a huge deal. It was the idea that the rules of physics up in the heavens were the same as the rules right here on Earth. Okay, to really get how this works, think about whirling a stone tied to a string. You've got the string and it's constantly pulling the stone inward, right? It's forcing it to move in a circle. That inward pull, that's what we call a centripetal force. It's center seeking. Now, what happens if you let go? The force is gone and that stone just zips off in a perfectly straight line. And that is exactly what's happening with the moon. It wants to go in a straight line, but the Earth's gravity is acting like a giant invisible string. That gravitational pull is the centripetal force, constantly tugging the moon toward us, bending its path into that familiar orbits. So, in a way, the moon is always, constantly, falling toward the Earth. Wild, right? But Newton didn't just stop there with the big idea. He actually gave it a mathematical voice. So now, let's check out the universal law he came up with, an equation that really does govern the whole cosmos. This is the core principle, and it is just profound. It's not just about planets and stars. It's everything. It means you, the screen you're looking at, your coffee cup, every single thing with mass is pulling on every other thing. So the law itself boils down to two main rules. Rule number one, mass matters. The bigger the objects, the stronger the pull. Simple. Rule number two, distance matters. A lot. The force gets weaker the farther apart things are, and it gets weaker really, really fast. It's what's known as an inverse square relationship. And here it is, the beautiful formula that puts it all together. F is the force of gravity we're trying to find. The big M and little m are just the masses of our two objects, and d is the distance between them. But that G is the special ingredient. So G is the universal gravitational constant. And just look at how incredibly tiny that number is. That's 10 to the power of -11. It's practically zero, and that is why you don't feel the gravitational pull from, say, your desk. The force is there, but since our masses are so small, the force is just way too weak to notice. You really need something planet-sized for gravity to become the main event. I mean, this sheer power of this one law is just staggering. It suddenly explained mysteries that had puzzled people for thousands of years. It's why we're stuck to the Earth, it's why the moon orbits us, it's why the planets orbit the sun, and it even explains the rhythm of the ocean tides, all caused by the pull from the moon and the sun. All right, let's pull this universal force out of the cosmos for a minute and see how it works right here in our own backyard. Now, when a physicist talks about free fall, they mean something very specific. It's this ideal situation where the only thing acting on an object is gravity. So to really see what gravity's doing, we have to pretend for a second that there's nothing else, like air, getting in the way. So gravity doesn't just pull things down, it actively makes them speed up. That's acceleration. Here on Earth, that acceleration has a special name, g, and it's about 9.8 meters per second squared. What that means is that for every single second something is falling, it gets faster by another 9.8 meters per second. And this leads us to a really weird conclusion, one that Galileo famously explored. In a true freefall, an object's mass makes no difference at all.
A heavy bowling ball and a light feather, if you drop them where there's no air, will hit the ground at the exact same moment. Of course, you know from experience that a stone drops way faster than a sheet of paper. So what gives? Well, it's air resistance. The paper is big and flat, so it catches the air like a parachute, creating a drag that fights against gravity. But if you could suck all the air out of the room, like in a vacuum chamber, yep, they'd fall side by side perfectly in sync. This all brings us to a really common mix-up. We toss around the words mass and weight like they're the same thing, but in the world of physics, they are totally, completely different. Okay, let's break it down. Mass is how much stuff is in an object. It's a measure of its inertia, how hard it is to get it moving. Your mass never changes, doesn't matter if you're on Earth or Mars. But weight is a force. It's the measurement of how hard gravity is pulling on all your stuff. And since gravity is different in different places, your weight can change. And here's the perfect example. The moon is much smaller and less massive than Earth, so its gravity is way weaker, only about 1/6 as strong. So if you went to the moon, your mass, the amount of you, would be exactly the same. But your weight, you'd weigh only 1/6 what you do here. You'd feel incredibly light. Okay, for our last section, let's check out some really cool effects that happen because of gravity's downward pull when things are in fluids, like water or even air. Your weight is a force pushing down on the floor. Pressure is all about how concentrated that force is. If you take that force and focus it on a tiny area, like the point of a nail, you get a ton of pressure. But if you spread that same force out over a big area, like when you wear snowshoes, the pressure is very low. It's exactly why a sharp knife cuts and a dull one just squishes. So check this out. When you put something in water, gravity is still pulling it down, of course, but the water actually pushes back up. This upward push has a name, the buoyant force. It's the reason you feel lighter in a swimming pool, and it's the absolute key to understanding how a giant ship made of thousands of tons of steel can just float on the ocean. So we've seen how gravity is the puppet master for everything from falling apples to spinning galaxies. But let me leave you with one final, kind of mind-bending thought. Out of the four fundamental forces in nature, gravity is, by a long shot, the absolute weakest. Seriously, think about it. A tiny little fridge magnet uses electromagnetism to easily beat the gravitational pull of the entire planet Earth. So how can a force that's so incredibly weak also be the one responsible for holding entire galaxies together? Well, that paradox, that's one of the biggest and deepest mysteries in all of physics.